Situation Report, Atlantic Theater, 1st of June, 1943. During the month of May, the Kriegsmarine's U-boat arm lost 41 submarines. 41 pressure hulls carrying approximately 2,000 officers and enlisted men were destroyed in 30 days. The previous monthly average for the preceding 12 months had been 13 boats. The May figure represented a 300% increase in the destruction rate, a statistical discontinuity so severe that it did not represent an escalation of existing trends. It represented the onset of a new condition. Grand Admiral Karl Dönitz, commander of the U-boat force and, since January of that year, commander-in-chief of the entire Kriegsmarine, recognized the anomaly immediately. On the 24th of May, he issued the order to withdraw all Wolfpacks from the North Atlantic convoy routes. The boats were recalled to patrol areas south and west of the Azores, where Allied air coverage was thinner, or returned to French Atlantic ports for refit. The withdrawal was described in internal communications as temporary, a pause to identify the cause of the losses and develop countermeasures. It was not temporary. The Wolfpack campaign against the North Atlantic convoy routes, the strategic centerpiece of Germany's naval war, never resumed at its former intensity. The decision made on the 24th of May was a doctrinal capitulation, even if Dönitz refused to frame it in those terms. The critical question, the question that consumed the Kriegsmarine's Signals Intelligence Service, its scientific advisory boards, and Dönitz himself, was a simple one. How were the boats being found? The U-boat's primary survival mechanism was invisibility. A Type 7C submarine on the surface presented a visual profile of approximately 3 meters height, the conning tower and periscope standards above a hull that set barely above the waterline. At night, in the open Atlantic, this profile was invisible to the naked eye beyond a few hundred meters. In fog, rain, or heavy seas, even less. The submarine's operational cycle depended entirely on this invisibility. It transited on the surface at night or in poor visibility, running its diesel engines to recharge batteries and make speed toward the convoy intercept line. When it detected a convoy, typically through Dönitz decrypted routing signals, it tracked on the surface, positioning ahead of the convoy's projected course. It submerged to periscope depth for the attack run, fired its torpedoes, and dove deep to evade the escort's ASDIC sonar. The entire tactical model assumed that the submarine was undetectable on the surface at night. By May of 1943, this assumption was catastrophically wrong. U-boats were being attacked on the surface, at night, in zero visibility, by aircraft that gave no warning of their approach. The boats reported no visual contact with the attacking aircraft before the depth charges were already falling. There was no searchlight illumination until the final seconds, sometimes not at all. The boat's Metox radar warning receivers, the FUMB-1, a crude search receiver designed to detect metric radar emissions, were silent. The operators heard no warning tone. The Metox indicated no incoming radar energy. The boats believed they were electronically invisible. And then they were dead. Dönitz's operational analysis staff examined 3 hypotheses to explain the losses. The first was that the British had broken the Enigma cipher, that convoy routing and Wolfpack positions were being read from decrypted U-boat signals traffic. This hypothesis was correct, but Dönitz and his communications security officers rejected it. They had examined the Enigma system and concluded that its mathematical complexity, the product of rotor settings, plugboard configurations, and ring positions, rendered it unbreakable. This was a failure of institutional arrogance, but it was not the primary cause of the May losses. The second hypothesis was that the British had developed a new form of radar operating on a wavelength too short for the Metox receiver to detect. This hypothesis was also correct, and Dönitz rejected it too, on the basis of advice from German radar scientists who assured him that generating sufficient power on centimetric wavelengths was a physical impossibility for an airborne system. The power requirements, they argued, could not be met by any valve technology compact enough to fit in an aircraft. They were wrong. They were wrong because they did not know about the Cavity Magnetron. The third hypothesis, the one that Dönitz and the Kriegsmarine scientific advisors accepted, was that the British had developed some form of infrared detection system, a heat-seeking sensor that could detect the thermal emissions of a submarine's diesel exhaust. This hypothesis was entirely false. No such system existed or was in development. It was a phantom, a technically plausible explanation that happened to be incorrect in every particular. And while the Kriegsmarine scientists chased this phantom through the summer and autumn of 1943, the 10-centimeter radar continued to kill their boats. The OODA loop, Observe, Orient, Decide, Act, of the Kriegsmarine's High Command was running on data from 1941. Their observation was filtered through institutional assumptions about what was physically possible. Their orientation was distorted by the belief that their own technology, the Metox receiver, provided comprehensive electronic surveillance. Their decision-making was poisoned by the false infrared hypothesis, and their actions, tactical countermeasures based on incorrect threat assessment, were useless against the actual threat. They were cycling through a decision loop that was decoupled from reality, and every cycle consumed time that cost submarines. To understand why the 10-centimeter revolution was lethal, you must first understand why the metric radar was survivable. The first generation of airborne anti-submarine radar deployed by RAF Coastal Command was the ASV Mark II, Air-to-Surface Vessel Mark II, operating at a frequency of approximately 200 MHz, corresponding to a wavelength of 1.5 meters. This system entered service in late 1940 and was progressively fitted to Coastal Command's Hudson, Whitley, Wellington, and Sunderland patrol aircraft through 1941 and 42. The ASV Mark II used a set of Yagi dipole antenna arrays, horizontal elements mounted along the wings and fuselage of the aircraft, to transmit and receive pulses of radio frequency energy. When a transmitted pulse struck a reflective target, a ship, a surface submarine, or even a large wave crest, a portion of the energy was reflected back to the receiving antenna. The time delay between transmission and reception gave the range. The relative signal strength between the port and starboard antenna arrays gave a rough bearing. Against a surface submarine at night, the ASV Mark II provided detection at ranges of approximately 5 to 8 miles, depending on sea state and atmospheric conditions. This was a significant tactical advantage. An aircraft equipped with ASV Mark II could locate a surfaced U-boat in total darkness, fly toward it, illuminate it with the Lee light, a carbon arc searchlight producing approximately 22 million candle power, mounted in a retractable housing under the aircraft, and attack with depth charges before the boat could fully submerge. However, the 1.5 meter wavelength had two critical limitations. The first was resolution. The ability of a radar to distinguish a target from surrounding clutter, wave returns, rain, sea spray, is a function of wavelength. Longer wavelengths produce broader beam patterns and lower angular resolution. The ASV Mark II's beam width was approximately 15 degrees, meaning that at a range of 5 miles, the radar's resolution cell was over a mile wide. A submarine's conning tower, presenting a radar cross-section of perhaps 2 to 3 square meters, was a marginal target embedded in a vast field of sea surface return. In rough seas, anything above sea state 3, the clutter overwhelmed the target return at ranges below 2 miles. The ASV Mark II frequently lost contact during the final approach, precisely when the crew needed guidance most. The second limitation was that the 1.5 meter wavelength was detectable. Radio waves at 200 MHz are straightforward to receive. The antenna dimensions required are manageable. A half-wave dipole for a 1.5 meter signal is approximately 75 centimeters long, easily fitted to a submarine's conning tower. The receiver electronics, simple crystal diode detectors with audio amplification, are uncomplicated. By mid-1942, the German Signals Intelligence Service, the Nachrichtenmittelversuchskommando, later designated the Wissenschaftlicher Beobachtungsdienst, had analyzed, captured, or recovered ASV Mark II components and understood its operating parameters. They developed the FUMB-1, codenamed Metox, after the French firm that manufactured the initial production units. The Metox was, by the standards of electronic warfare, a rudimentary device. It consisted of a simple broadband receiver covering the frequency range of approximately 100 to 500 MHz, connected to a crude antenna, the infamous Biscay cross, a wooden frame wrapped with wire in a cruciform dipole pattern. The Biscay cross was mounted on the conning tower when the boat was surfaced and had to be manually removed and brought below before diving. a process that added approximately 30 seconds to the crash dive sequence. The receiver fed an audio tone to the operator's headset. When ASV Mark II transmissions were detected, the operator heard a distinctive rhythmic pulse, the pulse repetition frequency of the radar. The stronger the tone, the closer the aircraft. The Metox worked. Against the ASV Mark II, it worked with devastating effectiveness. A surfaced U-boat could detect the ASV Mark II's transmissions at ranges of approximately 20 to 30 miles, far beyond the radar's own detection range of 5 to 8 miles. The submarine had a warning margin of 10 to 20 miles. This gave the crew ample time to disassemble the Biscay Cross, stow it below, clear the bridge, and execute a crash dive to safe depth before the aircraft arrived. The radar had been neutralized by the search receiver. The 1.5 meter game was over. Between the introduction of Metox in the autumn of 1942 and the spring of 1943, night kills by Coastal Command aircraft declined sharply. The U-boats were diving before the aircraft arrived. The lee light was illuminating empty ocean. The Bay of Biscay transit routes, where U-boats were most vulnerable, running on the surface between French ports and the open Atlantic, became survivable again. Dönitz's staff noted the improvement in survival rates and attributed it correctly to Metox. They concluded incorrectly that the electronic warfare problem had been solved. The British radar operated on metric wavelengths. The Metox detected metric wavelengths. As long as those two facts held, the U-boat retained its ability to detect and evade airborne radar. Those two facts ceased to hold in February of 1943. The Cavity Magnetron is a vacuum tube, but calling it a vacuum tube is like calling a nuclear reactor a heater. It is technically accurate and completely inadequate as a description of the device's significance. The operational challenge that the Cavity Magnetron solved is a problem of physics. To generate radar energy at centimetric wavelengths, 10 centimeters corresponds to a frequency of 3,000 megahertz, or 3 gigahertz. You need an oscillator that can produce high-power radio frequency pulses at that frequency. Conventional vacuum tubes, triodes, tetrodes, pentodes, work well at frequencies up to a few hundred megahertz. Above that, their performance collapses. The physical dimensions of the tube's internal elements, the cathode, grid, and anode, must be smaller than the wavelength being generated, and at centimetric wavelengths, the required dimensions push against the manufacturing tolerances of 1940s electronics. The electron transit time between cathode and anode becomes a significant fraction of the oscillation period, and the tube cannot sustain oscillation. The klystron, an alternative microwave tube developed at Stanford, could generate centimetric energy, but at power levels of milliwatts to a few watts. This was sufficient for laboratory work and communications. It was utterly insufficient for radar, which required peak pulse powers of tens of kilowatts to produce a detectable return from a small target at combat ranges. The Cavity Magnetron solved this problem through an elegantly violent mechanism. The device consists of a solid copper anode block, a cylinder approximately 12 centimeters in diameter, with a series of cylindrical cavities machined radially into its inner surface. A standard cathode runs down the central axis. A powerful permanent magnet, or in later models an electromagnet, generates a magnetic field parallel to the cathode axis. When high voltage is applied between cathode and anode, electrons are emitted from the cathode and accelerated toward the anode. The magnetic field curves their trajectories into spiraling paths. As the electron cloud sweeps past the openings of the resonant cavities, it excites electromagnetic oscillation within the cavities at a frequency determined by their physical dimensions, specifically their diameter and depth, which define the resonant frequency of each cavity acting as a tuned circuit. The critical innovation is the slot coupling between adjacent cavities. Each cavity's resonant field couples to its neighbors through narrow slots in the anode block, establishing a coherent, phase-locked oscillation across all cavities simultaneously. The electron cloud delivers energy continuously to this oscillation as it spirals past the cavity openings. The result is a self-sustaining, high-power microwave oscillator capable of generating peak pulse powers measured in kilowatts and eventually megawatts at frequencies in the 3 gigahertz range. The original Cavity Magnetron that changed the course of the Atlantic War was the number 12 design, developed by John Randall and Harry Boot at the University of Birmingham in February of 1940. It measured approximately the size of a man's fist. In its initial laboratory test, it produced 400 watts of continuous power at a frequency of 3 gigahertz, a wavelength of 10 centimeters. This was 100 times more power than any existing centimetric oscillator. Within months, production versions were generating peak pulse powers of 10 kilowatts. By 1942, Magnetron Type E1189, the production standard for airborne radar, was producing 50 to 70 kilowatts of peak pulse power at a frequency of approximately 3 gigahertz. By the end of the war, magnetrons producing 2 megawatts at peak were in production. The Cavity Magnetron weighed approximately 1 kilogram. It fit in a shoebox, and it produced more microwave power than the entire German Centimetric research program would achieve before the war's end. The Tizard mission of September 1940, in which a British technical delegation carried a Cavity Magnetron prototype across the Atlantic to share with American scientists, has been called the most significant single item of scientific cargo ever transported. The American industrial base, once given the magnetron design, scaled production to thousands of units. The radiation laboratory at the Massachusetts Institute of Technology, the RAD Lab, devoted over 3,000 engineers and physicists to developing radar systems based on the magnetron. The H-2S airborne ground mapping radar, the ASV Mark III anti-surface vessel radar, the SCR-720 naval fire control radar, and dozens of other systems flowed from this single device. The ASV Mark III, the weapon that killed the Wolfpacks, was the direct descendant of the Cavity Magnetron. It operated at a frequency of approximately 3 gigahertz, a wavelength of approximately 9.7 centimeters. Its antenna was a parabolic dish approximately 28 inches in diameter, mounted in a radome beneath the aircraft's fuselage. The parabolic dish produced a narrow beam, approximately 6 to 8 degrees wide, that concentrated the transmitted energy into a focused pencil, rather than the broad floodlight pattern of the Yagi arrays used by ASV Mark II. The narrow beam width had 2 immediate tactical consequences. First, resolution. The ASV Mark III could distinguish a submarine conning tower, a target with a radar cross-section of 2 to 3 square meters, from sea clutter at ranges where the ASV Mark II was blind. In moderate seas, the Mark III could detect a surface submarine at ranges of 8 to 12 miles and track it through to visual or lee light range without losing contact. The sea surface return, while still present, was distributed across a narrower beam, reducing the clutter power relative to the target return. The signal-to-noise ratio improvement was roughly proportional to the square of the ratio of beam widths. The Mark III's 6-degree beam versus the Mark II's 15-degree beam, yielding an improvement factor of approximately 6 to 1. This was the difference between a marginal target lost in noise and a solid, trackable contact. Second, and more critically, the 10-centimeter wavelength was invisible to the Metox. The Metox FUMB1 receiver was designed to cover the frequency range of 100 to 500 megahertz, the metric band. Its Biscay cross antenna was a half-wave dipole dimensioned for 1.5 meter wavelengths. A half-wave dipole for a 10-centimeter signal would need to be 5 centimeters long. The Biscay cross was 75 centimeters. The physical mismatch meant that the Biscay cross was almost completely transparent to 3 gigahertz energy. Even if some residual coupling occurred at the antenna, the receiver's intermediate frequency amplifiers and detector circuits were tuned for metric signals. A 3 gigahertz signal would not be processed. It would not produce a tone in the operator's headset. The Metox would sit silent while the ASV Mark III illuminated the submarine with enough microwave energy to track it from 12 miles to 0. The U-boat crew would hear nothing, see nothing. The operator would report, "Metox clear." The watch officer would confirm that the electronic warfare situation was permissive. The diesels would continue to pound. The batteries would continue to charge. And 6 miles away, closing at 160 knots, a Wellington or Sunderland or Liberator would be watching the submarine as a bright, crisp, unambiguous return on the planned position indicator scope. The bright green dot tracking steadily across the dark screen, range decreasing with each sweep of the antenna. The gap between the submarine's electronic awareness and the aircraft's sensor capability was not a disadvantage. It was a chasm. The U-boat believed it was operating in a 1.5-meter electromagnetic environment, where its Metox receiver provided 10 to 20 miles of warning. It was actually operating in a 10-centimeter electromagnetic environment, where it had 0 warning. The submarine's entire threat model, the doctrinal assumptions about detection, warning time, and evasion, was predicated on a wavelength that no longer constituted the primary threat. The German scientific establishment bears direct responsibility for this gap, and the mechanism of their failure is worth examining in forensic detail, because it illustrates how institutional assumptions can metastasize into operational catastrophe. German radar technology in 1943 was not primitive. The Telefunken Company had produced the Würzburg radar, a ground-based fire control system operating at 560 MHz, a wavelength of 53 centimeters. This was a sophisticated system, and it operated in the decimetric band, not centimetric, but well above the metric frequencies of early British radar. The Germans understood short-wavelength radar in principle. They had working systems in the ultra-high frequency range. What they did not have was the Cavity Magnetron. Their centimetric research relied on klystron oscillators producing milliwatts of power, sufficient for laboratory demonstrations, insufficient for airborne radar. German physicists were aware that centimetric radar was theoretically possible. What they believed and communicated to the Kriegsmarine with the confidence of institutional authority was that the power generation problem was intractable. They believed that no existing technology could produce the kilowatts of peak pulse power required for a practical centimetric airborne radar. They dismissed the possibility because they could not solve the problem themselves, and they assumed that if they could not solve it, no one could. This was not a failure of physics. It was a failure of imagination constrained by institutional pride. When the first intact H-2S radar set was recovered from a downed RAF bomber near Rotterdam in February of 1943, the German electronics team that examined the wreckage found the Cavity Magnetron. They measured its output. They analyzed its construction. They understood immediately what it was and what it meant. The technical report, circulated within the Telefunken organization and forwarded to the Kriegsmarine, made the implications explicit. The British had achieved high-power centimetric radar in an airborne package, and the existing Metox search receivers could not detect it. This report reached the Kriegsmarine's technical staff in March of 1943. Black May began in May. The interval, approximately 2 months, was consumed by institutional inertia, interdepartmental disputes about the report's significance, and the continued dominance of the infrared detection hypothesis within Dönitz's advisory circle. Even after the physical evidence of the Cavity Magnetron was in German hands, the operational response was delayed by the bureaucratic friction of a military-industrial complex that had committed to the wrong answer. The tactical reality of a centimetric radar attack on a surfaced U-boat at night can be reconstructed from operational records with reasonable precision. The following is a composite drawn from multiple after-action reports filed by coastal command crews during the spring and summer of 1943. A Wellington bomber of No. 172 Squadron, Coastal Command, is flying a patrol over the central Bay of Biscay at an altitude of 1,500 feet. The time is approximately 0200. There is no moon. Cloud base is at 3,000 feet. Visibility beneath the cloud layer is approximately 2 miles in intermittent rain. The navigator radar operator is monitoring the ASV Mark III display, a circular plan position indicator scope approximately 8 inches in diameter with a rotating radial sweep line. The scope shows sea return as a fuzzy band of green noise in all directions, with the aircraft at center. At 0213, the operator observes a discrete return at a range of approximately 9 miles, bearing 350 relative. The return is brighter than the surrounding sea clutter, and it does not correlate with any known fixed object. No landmass, no convoy route marker. The return maintains a consistent position and does not exhibit the wandering characteristic of a large wave crest or a rain squall. The operator reports a possible submarine contact. The pilot alters heading toward the contact. The operator continues to track. The return strengthens as range decreases, consistent with a hard metallic target, a conning tower and hull presenting a reflective surface above the waterline. At 6 miles, the return is solid and unambiguous. The operator confirms. Submarine, surfaced, heading approximately 270, speed estimated at 8 to 10 knots based on successive range and bearing plots. The pilot descends to 500 feet. He reduces speed to approximately 140 knots. The bomb aimer arms the depth charges, typically 6 Mark 11 depth charges, each containing 170 pounds of Torpex, a high-explosive compound 50% more powerful than TNT by weight. The charges are set to detonate at a depth of 25 feet, shallow enough to damage or destroy a submarine caught on the surface or in the first seconds of a crash dive. At 1.5 miles, the pilot activates the Lee light. 22 million candle power of carbon arc searchlight stabs through the darkness, illuminating a cone of ocean ahead and below the aircraft. In the center of the cone, exactly where the radar indicated, is a Type 7C U-boat, gray hull glistening wet, conning tower fully exposed, diesels trailing exhaust. The bridge watch is visible, 2 or 3 figures in foul weather gear. The interval between Lee light illumination and depth charge release is approximately 15 to 20 seconds. In those seconds, the bridge watch must do the following: identify the source of the light as an aircraft, shout the alarm, begin the crash dive sequence by ordering all hands below, closing the upper conning tower hatch, flooding the ballast tanks, and putting the bow planes to maximum dive angle. The Type 7C's crash dive time, from the moment the alarm sounds to the boat reaching a depth of 25 meters, is approximately 25 to 30 seconds under optimal conditions. Optimal conditions require the bridge to be cleared instantly, the hatch to seal on the first attempt, and the diesel engines to be clutched out and the electric motors engaged without delay. 15 to 20 seconds of warning is not enough. The boat is still on the surface or barely awash when the depth charges enter the water. 6 charges, dropped in a stick pattern across the submarine's estimated track, detonate within seconds of entering the water. The Torpex charges generate overpressure waves of approximately 4,000 pounds per square inch at 10 meters from the detonation point. The Type 7C's pressure hull, designed to withstand a maximum sustained pressure equivalent to a depth of approximately 200 meters, roughly 300 pounds per square inch, cannot survive a close proximity Torpex detonation. Hull failure, flooding, or severe structural damage results. The boat is killed or permanently disabled. And here is the forensic detail that matters. At no point during the approach, from the initial detection at 9 miles to the Lee light illumination at 1.5 miles, did the submarine receive any electronic warning. The Metox sat silent. The operator heard no tone. The search receiver, scanning its designed frequency range of 100 to 500 megahertz, found nothing, because there was nothing to find in that band. The 3 gigahertz ASV Mark III energy washing over the submarine's conning tower, perhaps a milliwatt of received power at the target, was outside the Metox's operational envelope. It was present and undetected. It was there and invisible. The submarine was tracked, closed, illuminated, and killed in a continuous sequence that began 9 miles away and ended with depth charges falling alongside the hull, and the submarine's only electronic warfare sensor reported clear skies throughout. This is not an ambush in the traditional sense. An ambush implies that the attacker conceals their presence. The ASV Mark III did not conceal its presence. It was transmitting actively, broadcasting 50 kilowatts of peak pulse power into the atmosphere with every pulse. The energy was there to be detected, but the submarine did not have a receiver capable of detecting it. The attacker was working in the open. The defender was blind to the frequency. In the month of May 1943, Coastal Command and U.S. Navy patrol aircraft sank or contributed to the sinking of 25 U-boats. Escort groups, destroyers, corvettes, and frigates protecting convoys accounted for the remainder. Many of those kills also facilitated by shipborne centimetric radar sets, such as the Type 271, a Royal Navy 10-centimeter radar derived from the same Magnetron technology. The
radar
total,
contact,
41
heading.
boats lost, was unprecedented.
Turbulence ahead, preparing
descent. The statistical
descent.
inflection is visible across multiple metrics. U-boat exchange rates, the number of merchant ship tons sunk per U-boat lost, collapsed from approximately 100,000 tons per boat in November 1942 to approximately 6,000 tons per boat in May 1943. The operational calculation that had sustained the Wolfpack campaign, the assumption that each U-boat would sink enough tonnage to justify the cost of the boat and its crew, became negative. The U-boats were being destroyed faster than they could inflict damage. The campaign was consuming submarines at a rate that exceeded the ability of German shipyards to replace them. And, more critically, it was consuming trained crews at a rate that exceeded the ability of the training establishment
range
to
12
produce
miles.
them.
Confirmed. It's
A
moving fast.
U-boat crew represented 14
New contact
to
bearing
18 months
090
of
closing in.
specialized
Roger.
training.
Monitor report to
The
command.
submarine itself could be built in 6 to 9 months. The human capital was the binding constraint. The convergence of the ASV Mark III with the Lee Light created what Coastal Command's operational research section described as a zero visibility kill zone.
Adjusting for current.
In the Bay of Biscay transit area, the waters between the French Atlantic ports of Brest, Lorient, Saint-Nazaire, and La Pallice in the open Atlantic, every surface submarine was now detectable at ranges of 8 to 12 miles in any visibility condition at any time of day or night. The transit, which previously required approximately 4 to 5 days on the surface to cross the bay, became lethal. Multiple submarines were attacked during a single transit. Some were attacked multiple times. A boat that survived one aircraft attack might surface to assess damage and charge batteries, only to be detected and attacked again by a second aircraft. Dönitz's response, ordering the boats to transit the bay submerged, traded one problem for another. A Type 7C at periscope depth on electric motors made approximately 4 knots. The bay transit that took 4 days on the surface now required 12 to 15 days submerged, assuming the batteries could sustain the load, which they could not without periodic surfacing. The operational tempo of the Wolfpack campaign, the ability to concentrate boats rapidly on a detected convoy, was destroyed by the transit time alone. Boats arrived on station with depleted supplies and exhausted crews. The concentration and attack cycle that Dönitz's Wolfpack doctrine depended on became logistically unsustainable. The Wolfpack concept, the coordinated mass attack on a convoy by multiple submarines, directed by shore-based radio control from Kenneth and later from Berlin, required 2 enabling conditions. First, the boats had to be able to concentrate from dispersed patrol lines, which required surface transit at 12 to 17 knots. Second, the boats had to shadow the convoy on the surface to maintain contact, reporting the convoy's position, course, and speed by radio to BDU, Befehlshaber der Unterseeboot, the U-boat command, which would then vector additional boats to the intercept. Both activities, surface transit and surface shadowing, required the submarine to be on the surface. Both were now suicidal. The surface transit was killed by the ASV Mark III in the Bay of Biscay. The surface shadowing was killed by the same radar in the convoy escort groups. The escort carriers, small converted merchant ships carrying 12 to 18 Swordfish, Wildcat, or Avenger aircraft, and the escort group's own 10-centimeter naval radar, ensured that any submarine that surfaced within 50 miles of a convoy was detected and prosecuted. The submarine could not get to the convoy undetected, and it could not shadow the convoy to enable the pack concentration.
Update hostile vessel at
The
Sector 7.
two
Designate kill.
prerequisites for the Wolfpack,
Prepare intercept.
surface
Launch in 2.
mobility and surface
Status report.
persistence,
All stations.
were both eliminated by the same technology, the Cavity Magnetron and its 10-centimeter radar offspring. The U-boat remained a dangerous weapon in individual submerged attacks. Its torpedoes could and did sink merchant ships through the remainder of the war. But the Wolfpack, the coordinated multi-boat surface-directed mass attack that had brought Britain to the edge of starvation in the winter of 1942 to 43, was dead.
The southern flank is collapsing.
It was not defeated by a superior submarine,
Heavy, 30%
or by better
casualties. We need reserves.
sailors, or by
Center 12
improved
division.
convoy
Stabilize the line.
tactics.
Yes, sir. I'll issue
Though
the
all
orders.
of those factors contributed. It was defeated by a frequency shift of approximately 1.5 meters down to 10 centimeters, a shift that rendered the Kriegsmarine's entire electronic warfare architecture obsolete overnight. The German countermeasure response was too slow and too late. The Naxos radar warning receiver, the FUMB-7, designed to detect centimetric transmissions, entered limited service in the autumn of 1943, roughly 9 months after the ASV Mark III became operational. The Naxos was functional but crude, with a detection range that was only marginally greater than the range at which the submarine was already detectable by the radar it was trying to warn against. Its antenna, a small horn mounted on the conning tower, had to be manually rotated to scan different bearings, a laborious process in heavy seas. It provided some warning, but it did not restore the comfortable 10 to 20 mile margin that the Metox had provided against metric radar. The game had shifted. The U-boat was no longer the invisible hunter. It was the hunted. The snorkel, the retractable air mask that allowed the boat to run its diesels at periscope depth, avoiding the need to fully surface, was the Kriegsmarine's ultimate concession that the surface was no longer survivable. The snorkel worked. It reduced the submarine's radar cross-section to a target area of approximately half a square meter, the top of the mast above the waterline, which was difficult for even centimetric radar to detect reliably at long range. But the snorkel reduced speed to 6 to 8 knots, eliminated the commander's ability to observe the tactical picture from the bridge, and made the boat noisy, uncomfortable, and prone to mechanical failure. It was a survival adaptation, not a tactical advantage. The snorkel-equipped U-boat of 1944 was a fundamentally different weapon than the surface raider of 1941, slower, blinder, and incapable of the pack tactics that had defined the Wolfpack era. Final assessment. The U-boat campaign in the Atlantic was not decided by courage, seamanship, or tactical skill. These were present in abundance on both sides. It was decided by a copper cylinder the size of a man's fist, machined with 6 resonant cavities, seated in a magnetic field, and producing 50 kilowatts of pulsed microwave energy at a wavelength of 10 centimeters. The Cavity Magnetron was the technical mechanism by which the surface submarine, the dominant naval platform of the first 3 years of the war, was rendered operationally untenable. The Kriegsmarine's failure was not a failure of engineering. German radar technology was competitive through 1942. The failure was institutional. The German scientific establishment, when confronted with the hypothesis that centimetric airborne radar was possible, rejected it on the basis of their own inability to achieve it. This is a specific cognitive error, the assumption that the boundary of one's own capability is the boundary of what is physically achievable. The British, through the Randall and Boot Magnetron, had breached that boundary in February of 1940. The Americans, through the radiation laboratory at MIT, had industrialized the breach by 1942. The Germans did not learn of it until a magnetron was recovered from a crashed bomber in February of 1943. And even then, the institutional machinery of the Kriegsmarine, the advisory boards, the committee structures, the deference to senior scientific opinion, delayed the operational response by months. 41 boats lost in 30 days, 2,000 men. Not because the boats were poorly built. The Type 7C was a capable, well-designed submarine. Not because the crews were poorly trained. U-boat crews were among the most intensively trained combatants in any navy. Not because the tactics were flawed in principle. The Wolfpack concept was operationally sound against an enemy without centimetric radar. The U-boats lost because the electromagnetic environment shifted beneath them, from 1.5 meters to 10 centimeters, and their sensors, their doctrine, and their scientific advisory apparatus could not shift with it. They were destroyed by a frequency they could not detect, warned against by a receiver that could not hear it, and counseled by scientists who said it could not exist. The 10-centimeter wave did not care about any of those things. It propagated at 300 million meters per second, reflected off the conning tower, and returned to the receiver. And the aircraft that carried it adjusted course toward the contact. Briefing closed. Stay sharp.